Welcome back, scholars. Hope you're well. I am going to record a lecture on chapter 14, which is correlation and regression. The first part of this lecture, part one, will be detailing the correlation, and then we will move into part two to talk about the other side. Once we know if two variables are correlated, then can we begin to predict variables? Or predict a variable or dependent variable from an independent variable, okay? So we're going to talk about a few things today. First, we're talking about what a correlation is, why we use correlation. We'll also talk about the hypothesis testing and how we use correlation and hypothesis testing to determine if these relationships that we find between two variables is significant or not, okay? So we'll talk about that and then we'll get out of here. So this will be part one, and then part two will cover regression. All right. So again, welcome. We're going to talk about regression and correlation today. Specifically for part one, we'll talk about correlation. Okay, and we'll talk about the really important parts for the purposes of this lecture. Okay. Let's do this and let's get started. I'm going to open up. Where's a pointer? I'll just start here. All right. So again, just for today, we're going to talk about and understand the Pearson R of the correlation as we measure the variables relationships. We're also going to talk about, computing the Pearson R, the definition and the computational formula. And number three, we're going to use the interpret Pearson R and understand the assumptions and limitations behind it. And the last thing we'll talk about today is the hypothesis test about the population and correlation using a sample R. Okay, so just like with anything, the inferential statistics, we use our samples to then draw conclusions or inferences about the population, and that doesn't change with correlation. So we did the same thing with a t-test, with one-way ANOVAs, and now we're going to be talking about correlation and how we use a sample to then draw conclusions or inferences about the population. Okay, and then these are other outcomes that we'll cover in part two. I'm talking about other alternative forms of the correlation. We'll also talk about the regression and how we evaluate the significance of the regression equation once we have performed the regression. Okay, just tools you'll need. Obviously, when we talk about statistics, these skills that we have build on one another. We'll need to know about complex squares, the z-scores, hypothesis testing, and the analysis of variance, because all of this is tied together as we talk about looking at differences in relationships. Okay, so what is a correlation? Correlation, it measures relationship, okay, and it describes the relationship between two variables. It measures two different variables for each individual, and then you assess the relationship. Is the relationship a positive relationship or a negative relationship, or is there no relationship at all? And we'll talk about those different characteristics, okay? So the direction of the correlation is, again, talking about whether it's positive or negative. Okay, and when we talk about the correlation coefficient, you're going to see a positive number or a negative number. Positive number means that I have a positive correlation, meaning that as I increase one variable, the other variable increases. Or if I have a negative correlation relation, that means that one variable is increasing and the other variable is decreasing. Okay, these correlations also form what we call a linear. It's kind of a linear model, right? So it shows us at one variable, we have one participant, and we measure them at one variable, we measure them at the other variable, and we're measuring to see if there's some linear relationship between those variables, okay? The strength and the consistency, the correlation coefficient, it ranges from 0 to plus or minus 1. The higher, the closer your value is to 1, the stronger your correlation. And again, it doesn't matter the positive or the negative sign. The strength only refers to the value of that decimal, okay? And again, all of our characteristics are independent of one another. And again, as we talk about, those are some of the assumptions that we have to meet when we refer to a correlation. Okay, so here's an example of a correlation. As you can see, you have one person, and they are measured on two separate variables: family income, and then students' average grade. Okay, so you see you have several individuals, and then you plot those points on a graph. And what you see here, uh, this is considered a scatter plot. Okay, because each individual dot represents one person. Okay, so if we're looking at A, okay, they have a family income of $31,000, which is here, and they have the student's average grade is 72. Okay, and as you see, there is a positive relationship. This goes up and to the right, which means you have a positive relationship. As one, the family income increases, the grades or the student's average grade also increases. And you see that um, gradually there, right? So it's not a one-to-one, right? Because there are some variances, there's some variance there, there's some error, right? So just because you have a high income doesn't mean you're going to have high grades, but on average, you do see that relationship where the higher your income, the higher your grade on average, okay? Again, here is our examples of positive and negative relationships. Again, in the A example here, in graph A, you have performance in class, and you have time spent studying. So that's a positive relationship there. All right, these two variables are positively related because the more you study, the higher your grades or the performance in the class. In the B graph, right, you have performance in class and smartphone use, right? So there's a study that was done that showed that the more time you spend on your phone during class, the lower your performance is on the exams or in the class generally, right? So again, this shows a negative relationship. Again, these two variables are negatively related, right? So it goes down and to the right, and this one goes up and to the right for a positive relationship, right? Down and to the right for a negative relationship, okay? And then here, we're talking about the strength, right? We're talking about the strength, and this is my Pearson core R correlation, right? So this is a perfect negative correlation. That means with every change in the variable y, you have the same exact change in the variable x, and it's a perfect negative correlation. For graph B, right, there is no um, direction of the dots in the scatter plot, so it's considered to have a zero correlation. There's no correlation between variable A or variable Y, excuse me, variable X. You do see a stronger positive correlation here, right? The values are a lot more clustered together, right? And they're all going up and to the right, so you have a positive 0.9 correlation, right? So that means that there's a pretty strong correlation between variable X and Y, okay? For graph D, right, you see a negative correlation, negative 0.4. Again, that is not that strong of a correlation, but you do see a trend in the relationship and how it is slanted downward and to the right. All right. So again, when we talk about the Pearson correlation, right, the Pearson correlation, again, notated with the value of R, okay? It measures the degree and the direction of the linear relationship between the two variables, right? So we're talking about the negative positive relationship, plus or minus, and we're also talking about the strength. And the strength is that number that we got, okay? When we talk about a perfect linear relationship, every change in X has a corresponding change in Y. So either a perfect negative or a perfect positive, a value of 1 is that perfect correlation. There are not many variables that have a perfect correlation, right? So many times there are varying values for each variable, and so you rarely have a perfect correlation, okay? But again, the way we design the Pearson correlation coefficient in the numerator, we have how the X and the Y, how they covary together. I mean, how do they trend together, right? So that's in the numerator. And in the denominator, the variability of X and Y separately. So we're looking at the variance between Y and X variable separately. And then in the numerator, we're looking at them together. And I'll show you how we calculate those variables. Okay. So when we're looking at the numerator, we're looking at the covariability between the two variables. We're looking at the sum of the products of the deviations, right? This is very, very similar to what we saw in the sum of squares. And again, that's how we can relate a t-test to an ANOVA, to a correlation, because we're using very, very similar computations for variance and for t-test, we'll see later, okay? But again, this measures the amount of covariability between the two variables, and this is going to be going on the numerator of the formula, right? So SP, or the sum of products of the deviations, you have your X variable, you get the mean, and you, again, just like we did for all of our sums of squares, you take the deviation and you square it, and that gives you your sum of squares. And you're going to do the same thing for the X and the Y variable. So these would be considered your sums of squares, okay? And this is, again, the sum of squares between those two variables, or the core variability between those two variables, okay? So this was the definitional formula, right? This is done usually when you have whole numbers. Really, really easy to kind of calculate it in that way, right? But if you don't have whole numbers, the computational formula is probably the most accurate, right? Because it allows for you to have decimal places, right? The definitional formula kind of emphasizes the SP as the sum of those two differences. The computational formula results in, again, an easier calculation, especially if you're dealing with decimal places, right? So this would be considered my SP or my computational formula. And either one of these formulas is going to get you very, very similar answers, if not the same answer, just depending on the number of decimal places you use for your computations. Okay, so here's a scatter plot, right? Again, as we talked about before, again, each point represents one person or one participant, right? And so you have the x-axis, and you have the y-axis here on the left-hand side, and you have the y-axis, the x-axis that runs horizontally, the x-axis runs vertically. Okay. All right. So in order to get my Pearson R correlation, again, we have my SP. We know how to calculate the SP based on that, again, that sum of squares. And then in the denominator, we're calculating the variance separately. So we're looking at the sum of the squares for X and the sum of the squares for Y. You multiply those two things together, you take the square root, and that's how you get your denominator. And that's the variability between X and Y separately. And again, remember that S&P is the covariability between X and Y together, right? Here's an example of how you would calculate it, right? So you have scores for your X, you have scores for your Y, okay? They also got their means for X and Y, okay? And so what they did was they took the deviations for X, they took deviations for Y, and then they squared those deviations, right? They squared those deviations. So what you see here, this is the sum of squares. This is going to go in the denominator, right? So you have 64 here, you got 16 that goes here, and they, again, took those deviations here, they multiplied them together. So -6 times -2 gives me +12. 4 times 2 gives me 8. -2 times -2 gives me +4. 2 times 0 gives me 0. And 2 times 2 gives me 4, right? So they sum all of those together, and that becomes my SP. All right, so we take my SP, we divide that by the denominator, 32, and we get a correlation of a positive 0.875, which is a really, really strong positive correlation. That means value for the variable X and the variable Y are very, very strongly correlated, okay? But again, the computations are really, really simple. You're just plugging numbers in once you calculate your deviations, and then you get your products, the sum of the products, and you just plug in. Okay? So when we talk about the Pearson R correlation, you can also use z-scores to calculate your Pearson R for your sample, which is that R, and this is considered what we call the population or the row. So the row and the R are equivalent, just one notation is for the sample, and the other is for the population. We use z-scores and can use z-scores because z-scores tell us the location of our variables in a distribution. And since we want to know what the correlation is, we want to know what the location is. Is the location of X and the location of Y, are they kind of in the same location, right? Or are they in different locations? And if they're in different locations, then the correlation will vary. If they're in very similar correlations or in similar locations based on their z-scores, we know that they are highly correlated and you'll get a higher R. All right, so we can use z-scores, and these are the ways that you would get it, right? So you take your mean, you get your actual score for the X value, you divide it by your standard deviation, that gives you your z-score, right? You'll do that for all of your values, all your X values. You'll also do it for all your Y values. You multiply those products together for the z-scores, and you sum all those together, and you divide by the degree of freedom, right? So you take all of your participants, n minus 1, say you had 10 participants, 10 minus 1 gives me 9, and you place that here, right? For the population, you do the same thing for all of your scores. You're going to get the z-score for the Y and the X. You multiply those z-scores together, you sum those products together, and then you multiply by the total number of individuals in that population, right? So the only difference is the n minus 1, because I want to have a biased, unbiased statistic, right? That's why we do the n minus 1, okay? All right, a learning check. It says a scatter plot shows a set of data points that fit very loosely around a line that slopes down and to the right. Which of the following values would be the closest to the correlation for these data, right? So it says a scatter plot shows a set of data points that fit very loosely, loosely meaning the strength of the correlation is not that high. And it says down and to the right. And when I say down and to the right, I'm looking at a negative correlation. So if you pause the video, you should get a negative 0.35. Okay. Oh, excuse me. A negative 0.35. Again, very loosely around a line that slopes down and to the right is negative, and the strength of the correlation is very, very weak. Okay. True or false? It says a set of n equals 10 pairs. So we got 10 participants, 10 people of X and Y scores has a sum of X equals Y equals the product of X and Y equals 20. Okay. For this set of scores, SP equals negative 20. Okay. You'd have to do that calculation, and you should get an answer, and you'd be able to answer to see if that SP equals 20. Remember that you have your sums of products at the top. Okay. And again, how do we calculate that? Go back. SP is calculated. You can do it one of two ways. You could do it this way, right? So we knew that X and Y was 20. We knew that the sum of X was 20. We also knew that the sum of Y was 20, okay? And then we also know that this is 10, right? So with this being 10, you just do the math and you should get the answer, okay? For the second question, it says, if the Y variables decrease when the X variable decreases, then the correlation is negative, okay? All right, so the first one is true, right? Again, using the computational formula, you have 20 times 20 is 400, divided by 10 gives me 40, 20 minus 40 gives me a negative 20, so that is true, okay? The second one was false. If they, again, go in the same direction, they are positively correlated. If they go in different directions, right, that means they are negatively correlated. So they have, both of the variables go in the same direction, you know you have a positive correlation, right? So even if they both go negative, that means you have a positive correlation, okay? All right, so why do we use and how do we interpret the Pearson-R correlation, right? The Pearson-R correlation has various applications, and we're going to talk about 4 of them today. One of them is prediction, right? You can use one of the variables to make predictions about the other variable, right? So if I want to look at an ACT score, I can look at ACT scores and I can oftentimes predict college GPA, or I can use high school GPA to predict college GPA. And that's usually what happens. I can predict using one variable and the next. We looked at performance in the class and the amount of time studying. So I know that those students who spend more time during the week studying for the class, they're likely going to perform higher. Again, positive correlation. All right. We talk about validity. We use measuring. Are we measuring what we intend to measure? Right. So we have a new test of IQ, and we compare the values and the variables for that IQ test to other proven methods that were, or again, also calculating IQ. Are those IQ scores very, very similar? If they are, I know that I'm actually measuring IQ the way that I said I wanted to measure. Okay, so again, validity, intending to measure what I wanted to measure. Okay, reliability is another thing, right? Sometimes when we have an opportunity to do a survey, right, and I have an instrument that I want to test, okay, I want to see if it's consistent. So I have a person take an IQ test twice, the same IQ test, and I want to see if those IQ tests are very, very similar, right? And I do that for maybe 2 or 3 people, and I want to see if taking the same test twice gives me a very similar result. And if I see that I see those correlations, say I did a before and after X, and then Y, the X is the before the first test, the Y is the second test, and I gave that test to 100 people. Right? They took it twice, X and Y. I look at the correlation between the X and the Y. If that relationship is extremely high, I know that the IQ test is extremely reliable. That means that the scores don't change or vary much at all. Right? And then also the last thing is theory verification. All right, you want to test the theory by determining a correlation between the two variables. So just like in our previous example, we used time spent studying and academic performance. So now we know that we need to increase opportunities for students to study and encourage students' study skills so that they study more often. And then we know that if they study more often, then their grades will increase. Or does a parent's IQ predict their child's IQ, right? So we look at a parent's IQ, we look at the child's IQ for maybe 250 or 200, maybe say 200,000 people, right? And we want to see if that correlation is high, okay? Is there a positive correlation? Is it a negative correlation? We want to determine that if that's the case. Okay. But again, when we interpret correlations, I want you to, again, burn this into your memory, right? Correlation describes the relationship between two variables, but it does not determine and cannot demonstrate the causation, right? Because these two variables, there are so many extraneous variables to our life, right? Everything has an effect, right? And when we talked about the amount of variance that's accounted for by variables, again, we know that just because they are correlated doesn't mean that they control for everything that happens in the change of those variables, right? So again, correlation does not demonstrate causation. There are a few examples I like to use. There's one study or one correlation between the amount of shark attacks and the amount of ice cream consumed, right? Right. The amount of shark attacks increases. The amount of ice cream consumed also increases. It's very, very highly correlated, positively correlated two variables, right? What is the other variable that might influence that, right? The heat, right? During the summertime, more people go to the beach. So the incidences of shark attacks may increase, and more people are going to be eating ice cream because it's warmer outside, right? So that extraneous variable is the season, right? It's warm outside, and so you see things happening in the same direction, but doesn't mean that they cause one another to happen, right? So just because you eat more ice cream doesn't mean you're gonna suffer a shark attack, right? Again, it's just depending on the time of the year, right? So again, establishing causation, it really requires an experiment, right, in which one variable is manipulated and the other variables are controlled very, very closely, right? That's the only way that you can show causation between one variable, right? We'll look at example 4.4, but again, that demonstrates the kind of the fallacy of attributing causation after observing correlation, right? So you think about this, right? You got the number of serious crimes on the left-hand side here in your y-axis, and then you have the number of churches on the x-axis here, right? So it looks like as the number of churches increases, it looks like the number of serious crimes also increases. And that doesn't mean that those two things cause one another. You would hope that having more churches would decrease the number of serious crimes, right? And again, why is this? What may be the other factor or variable that might influence this relationship, right? That'll be something that you can think through. Like why the number of churches also increase the number of serious crimes, right? Churches are usually placed in various areas. Churches are everywhere, right? So churches have been increasing forever. It doesn't necessarily mean it's causing the number of serious crimes. Maybe we're living in a really large city, right? So the number of churches in a really large city, again, when you increase the number for the population, crime is going to increase, and the number of churches is also going to increase, right? So just by the size of the city, that may increase the number of churches, that may also increase the seriousness of crime. So again, that's that extra variable that we have to take into account. That might be one of those mediating variables that we take into account for why these variables are correlated. So this is a very strong, very strong relationship there, and it's a very strong positive relationship. Okay. One of the things that we might and may need to be really careful about is how the variables can be affected by a range of different scores, right? There are some instances where researchers sometimes restrict the values in their range, right? And when you severely restrict the range, it provides you with a very different correlation than would a broader range of scores, right? So if you just kind of limit to a particular set of scores, the correlation may not be as strong as if you were to, again, extend it out to a very broader range of scores. And I'll show you what that looks like. Right. So be safe, right? It says never generalize a correlation beyond the range of data presented or represented in the sample, because you don't know, right? If they only give you a restricted range, you don't know specifically, again, how that may play out if you extended that and beyond the range that is presented. Okay, so here's an example, right? So in the values here, you see a kind of a positive correlation here goes up and to the right, right? But with a restricted range, if you just restricted the range to these values here, there's no correlation whatsoever. It's a zero correlation. Here you see a pretty positive correlation, right? But if you just restrict it to this range and these X and Y values out here, then you see no correlation whatsoever, right? It's a zero correlation pretty much, right? So again, by restricting the range with this dotted line here, you do see a very different, like even if you restricted the range to these circles here, right? Very low correlation, no correlation whatsoever. Okay, and so be really careful about restricted range and how that affects your correlation. Okay. One of the things that we talk about with correlation is outliers, and outliers play a really particular, really strong role in how you can predict other variables, and they pull the correlation either very positive or very negative, depending on where that outlier lies. Okay, so an outlier again is any individual with X and Y values that are substantially different from other data in the sample, right? So take for instance, we have height, right? We're doing height and shoe size, right? For our two variables, right? In our class, in our statistics class, all of us have, I'm shorter, you all are shorter. But then what if I had a couple basketball players in our class, right? They would be an outlier. Maybe they're 6'8", 6'9", right? They would be an outlier, right? Our shoe sizes, our our heights are here, right? And then the outlier would be laying all the way out here because again, 6'8", 6'9", I'm under 6 foot, right? But again, those outliers again are characterized by much larger score than all the others in the sample, and that's usually what happens, right? So if I'm calculating or getting data, I have to be mindful of that, right? So I may want to remove the outliers so that I get a more true and more accurate correlation based on the data that I'm collecting. Okay, but again, it says outliers produce a disproportionately large impact on the correlation coefficient. Okay, so again, we got graph A. There's a very low correlation here, right? Negative Negative is not even a very, very strong correlation, but there is a slight correlation there, right? And again, this is the original data, right? But what if I added that outlier back in, right? Now I see a really, really positive, positive correlation up and to the right, right? 0.85, negative 0.08, right? You see how the outlier is drawing that correlation out and making it seem like it's more tightly correlated and related than they actually are, right? So if I had a research study and I saw this guy all the way out here, I probably would go ahead and remove him so that I could get a more accurate view of what that relationship is between the X and the Y values. Because again, it's disproportionately affecting this correlation coefficient by a great margin. Okay. So again, correlation and the strength of the relationship. Correlation and the measures of the degree of the relationship between the two variables. Again, it relies on a scale from 0 to 1, like we talked about. Okay, it is easy to mistake and interpret the decimal number as a percent or a proportion, and it's not, right? It's just showing me, it's just a number. It's on the decimal. It's on that scale, right? It's on that scale. Correlation is not a proportion. It's not a percentage, right? The only time that you will get it to become a proportion or a percentage is when you square, right? When you square the correlation, that is somewhat of an effect size for the correlation coefficient, right? Because what the correlation coefficient or the squared correlation does, it gives you that portion of that shared variability. It's the R squared that we've talked about in the t-test, in the ANOVA. It is the same, right? We're looking at the R squared, and that is our effect size, right? So we're looking at squared correlation. When you square it, it provides you with the portion of that shared variability, right? So if it is higher than 0.5, that means that 50% of the variability in the changes in the scores X and Y, that means that 50% is being explained by that relationship, right? And so that is a really, really high effect size and a really, really important way to describe it. The squared coefficient, the squared correlation, is also called the coefficient of determination, okay? So again, when we use the coefficient of determination, that is our effect size when we have calculated our correlation, okay? So again, coefficient determination measures the proportion, the variability, like we talked about before, that R squared. And then when you get the R squared, again, it's talking about how one variable is determined from the relationship with the other variable, okay? So we're really tied into that because when we look at maybe a correlation of 80 for our example here, that means that 64%, when I square 0.8, 64% of the variability in the Y scores can be predicted from the relationship with the X. And that's a really, really high correlation, right? That's a really, really big effect size. That means that those variables are really, really highly correlated and are related to each other in a very, very big magnitude. Okay. But again, coefficient of determination is the R squared, and that would be considered our effect size for the correlation. Okay. Here are, again, different degrees of linear relationship, right? So again, we look at IQ scores, shoe size, and that R squared for this one is going to be really, really low because, again, there's really no correlation whatsoever here, right? But you might see in graph B, you see that there's a positive correlation, right? Positive correlation between IQ scores on the x-axis and college GPA on the y-axis, meaning the higher my IQ, the better I do as far as college success as a proxy for college GPA, right? So I do see a positive R squared there. There might be some variability is explained in, again, your IQ score and how it can predict your college GPA, okay? And then your annual salary, your monthly salary, that is a perfect positive correlation. Again, the relationship between your monthly salary, again, is directly tied to your annual salary. Positive correlation, positive. So it's a positive one correlation, and you get a positive. It's taken 100%. 100% of the variability is explained by monthly and annual salary. Okay. One of the other things that we'll talk about, last thing we'll talk about is the hypothesis test. Okay. And when we talk about the Pearson correlation and the hypothesis test, it's done very much the same as we did for all of our other chapters, right? The first thing you're going to do is you're going to set your hypotheses. You're going to set your critical region. you're going to compute your statistics, and then you're going to make your decision. Okay, all of these are going to be done the same way in the correlation, right? So with the Pearson correlation, again, you're going to state your hypotheses. The population correlation is represented by the Greek letter rho. Okay, so when we're looking at stating our hypotheses, when we're looking at the null hypothesis, all that's going to say is that it equals zero. Zero meaning we're looking at a zero correlation, no correlation, no relationship whatsoever, right? And the alternative hypothesis, when we're talking about non-directional, it says that it is not equal to zero, meaning that there is some relationship either greater than or less than zero, right? When we're looking at the directional, right? This one right here says that there is a positive relationship, right? So the null hypothesis says that there is a negative relationship, negative or zero correlation to with the relationship with the population. And then the alternative hypothesis says for this first one that there is a positive relationship between the x variable and the y variable, and the opposite is true for this one, right? So it says that there's a positive or zero correlation, and then in this alternative says that there's a negative correlation, right? So you're doing a directional correlation for the directional hypothesis. Okay. One thing that we talk about when we're talking about the sample and the population, remember, as always, when we're taking a sample, there is always error that's associated with taking a sample out of the population, right? If you look at this is the population. This represents the population. It's got a population of scores for X and Y, right? This looks like it's zero population, zero correlation here, right? However, if I took a sample, and that's why they circle these, if I took a sample of three, N of three, right? You start to see that there is a more of a positive correlation, right? They're up and to the right, okay? So just because the population has a zero correlation, when you take those samples, the samples again are not going to always be zero, right? You're going to have some that are positive, you're going to have some that are negative, you're going to have some that don't have a correlation whatsoever. But once you average all those correlations up, it should average out to be a zero correlation. But again, there is some error. When you do take a sample, there is error. It doesn't match the correlation for the population 1-to-1, okay? Once you get your hypothesis test, again, one of the things that you do, we use the when we set our critical region, right? We're going to be using either a t-test or an f-test, and we're going to be using those distributions. Okay, you can use either, right? You can use either the t or the f. In the chapter that we're in, chapter 14, we're only going to be using the t, right? So you have to calculate the degrees of freedom. You're also given your significance levels. We oftentimes use a 5% significance level. So with a 5% significance level, and then you're going to do n-2 for these degrees of freedom because you have two variables, right? So if I had a sample size of 20, right, I would do n-2 or 20-2. That would give me a sample size of, or degrees of freedom of 18. I'd use that degrees of freedom. I'd find the again, the one-tailed test or the two-tailed test, depending on what we're looking for. If we're looking for non-directional, we use a two-tailed. If we're looking for directional, we use a one-tailed. And then I would calculate that critical region based on that t value, okay? This is how you calculate your t, right? So the first thing you're going to do is you're going to compute your R. We know how to compute our R. This value for rho is going to be 0. Okay, that's going to be our hypothesis, because our hypothesis says that the population correlation is 0, right? So we take this, we get our correlation minus 0, and we plug everything else in R squared, plug our n in here, which are degrees of freedom here, and then we calculate based on the values that we put in there. Okay. Here is an example. Okay, so it says a researcher is using a regular two-tailed test with an alpha level of 0.05 to determine whether a non-zero correlation exists in the population. Okay, so a sample of n, 30 individuals is attained and produces a correlation of R equals 0.35. Okay, so it's a very, very low correlation. Okay, but it is a positive correlation. Okay, the null hypothesis states that there is no correlation in the population, right? So this is my null hypothesis. The alternative hypothesis would say that rho is not equal to 0, that there is a difference, and we're looking at the significance of that difference. Okay. All right. So for this example, it says degrees of freedom is 28. So we have n equals 30. So again, when we talked about the degrees of freedom, that's n minus 2. So again, my degrees of freedom was 28 here. All right. So I'm using the 28. I go find that on the t distribution. Okay. In our, you have your handout. You find your t critical, which is plus or minus 2.048. And if you want to pause the video, go to your t distribution, that table, find again two-tailed test, 5 persistent Leviticus level, go down to 28 degrees of freedom, and then you should find a plus or minus 2.048. Okay. You have again your R squared, which is that you take the 0.35, you square it, and gives you 0.1225. Okay, you're gonna do all of that for, you're gonna plug all that in, and get a t value of plus or positive 1.98. Right, given my critical region here, plus or minus 2.048, and my actual t that I calculated, 1.98. My 1.98 does not exceed or is not greater than 2.048. So I know that this correlation is not significant or not, right? It's not, I don't have enough evidence to say that it is a significant correlation. Okay, it's not that great or not that much far off from zero correlation. Right? Had it been a little larger, then I would likely get a very significant correlation there. So since the t-value is not in the critical region, so we fail to reject the null hypothesis, the sample correlation is not large enough to reject the null hypothesis. So it's not a significant correlation. Okay. But again, had this been maybe 5% significant, or 0.5, right, correlation, then that might have given us a positive t, which then would have rejected the null hypothesis. Okay. All right. So after you do your hypothesis test, this is how you report your results. Right. It's really, really concise. All you're doing is reporting whether that correlation is statistically significant or not. Right. So you get the value of your correlation, which is here. Right. You get your sample size, which is n equals 30. Right. You get your proportion, your p-value, your probability value, which is p less than 0.01 or p less than 0.05, and then you just call it a t-tail or two tails, right? And if you wanted to do a your effect size, your r squared, then you would put comma and you would put r squared there. So if I decided to do that, let me go here. I would just go comma, and I would go r squared equals, right? Let me do 0.65 squared. Let me do that really quickly. So 0.65 squared, and that gives us something to squared, and that gives us an r squared of 0.4225. Okay, so that would be considered my effect size for this result. Okay, all right. But that is it. Okay, that is it. That is correlation. That's hypothesis testing. We talked about a lot of information. All the information is fair game on the exam. You may be given a little information that has to compute something, but it would be very, very simple. Okay? Very, very simple. I hope you enjoyed this. This is part one. Part two will explain some alternative forms or measures of correlation, and then also regression and how we begin to predict using various variables. Okay. All right. So we'll stop there. Hope you all have a great evening.